I am Professor Ajay Kumar Patnaik. I will teach today the angular wave function as well as the shape of the orbitals. As I have told you, the wave function is composed of two parts. One is the radial wave function and other is angular wave function. The radial wave function shows the behavior of the orbitals as I have shown you in last class. But angular wave function determines the shape of the orbitals. The angular wave function of s orbital will show what is the shape of s orbital. The angular wave function of p orbital will show what is the shape of p orbital, like this. So, let us see what is the angular wave function for s orbital. So, this angular wave function depends on L and m values. For s orbital, L is equal to 0 and m is equal to 0. So, the angular wave function is there are two types of angular wave function. One is a theta, other is a phi. When theta, I have told it is a zenith angle and phi is called azimuthal angle. When these two angles vary, the wave function varies. For s orbital, the theta wave function, the orbital theta angular wave function theta is equal to 1 by root 2 and phi is equal to 1 by root over 2 pi. 1 by root over 2 pi. So, theta and phi gives you the angular wave function for s orbital, which is equal to 1 by root over 4 pi. That is equal to 1 by 2 root pi, which is a constant quantity. That means this angular wave function product of both the angular wave function is a constant quantity. It is independent of theta and phi. That means along the three axes, the value is constant. So, it is spherical symmetrical. So, s orbital is spherical symmetrical. This is s orbital is spherical symmetrical. S orbital along three axes. Now, this is for 1s orbital. Now, if you consider the 2s orbital, it will look like this. So, there is a gap between 1s orbital and 2s orbital. This gap is called a node. Similarly, if you consider the 3s orbital, if you consider the 3s orbital, this is 1s, this is 2s, another this is your 3s orbital. So, these are the three gaps, 1 and 2. These two are the nodes region where the probability of finding the electron is 0. So, for 2s orbital, 1s orbital there is no node, for 2s orbital there is one node, and for 3s orbital there are two nodes, and all s orbitals are spherical symmetrical. Now, let us come to the p orbital, where p orbital L is equal to 1 and m is equal to plus 1, 0 and minus 1. So, these three values correspond to three orbitals. So, there are three angular wave functions corresponding to m plus 1, 0 and minus 1. So, this is the wave function, angular wave function corresponding to plus 1, that 3, 4 pi sin theta cos phi, represented by equation 1. Similarly, the orbital, the angular wave function for m is equal to minus 1 is represented by equation 2, that is 3 by 4 pi half sin theta sin phi. And third angular wave function corresponding to m is equal to minus 1 is equal to 3 by 4 pi half cos theta. So, its value depends on sin theta and sin cos phi. Its value depends on sin theta sin phi, and its value depends on cos theta. Now, if these wave functions we can convert into Cartesian coordinate, because it will be plotted against the Cartesian angular wave function will be plotted against the Cartesian coordinates. Therefore, it is converted, these values are to be converted into Cartesian coordinates. Now, x is equal to, so we have in polar coordinates conversion, we have already shown that x is equal to r sin theta cos phi, y is equal to r sin theta sin phi, and z is equal to r cos theta So, we can write x by r is equal to sin theta cos phi. So, x by r is equal to sin theta cos phi, y by r will be equal to sin theta sin phi, and z by r is equal to cos theta. So that means in this place we can put 3 by 4 pi constant, 3 by 4 pi half, and sin theta cos phi, against we can write x by r. Here we can write 3 by 4 pi constant, and in place of sin theta sin phi we can put y by r. Similarly, third equation we can write in place of cos phi we can write 3 by 4 pi half z by r. Now the angular coordinates, these three angular coordinates are converted into Cartesian coordinates x, y and z. So now the angular wave function is plotted against the coordinates x, y and z, will get the shape of, in a 3-dimensional space, gives the shape of the p orbitals. This corresponds to px orbital, this corresponds to the py orbital, and this corresponds to the pz orbitals. So if these angular wave functions, three angular wave functions are plotted against x, y, z in a 3-dimensional space, we will get the shape of the orbitals, shape of the p orbitals. Now in shape of the p orbital px, it gives a two dumbbell shape, it is px so this is the shape of px and py and pz. It is a dumbbell shape having the two lobes, one is a positive, other is negative. One is positive, other is negative. One is positive, other is negative. Then why this is positive and this is negative? Now this depends on the value of theta. Let us see pz orbital, let us see this orbital, pz orbital. So the pz orbitals depends on z by r into cos theta. So pz orbital is equal to, that is equal to theta, pz orbital that is equal to theta 0 and phi 0 is equal to z by r cos theta. So this is your pz orbital. It depends on the angle theta. Let us see this equation. Now for cos 0, this is the point pz orbital. Why this is positive and why this is negative? This is a pz orbital. Now this point is cos 0. Cos 0 is equal to 1. And this point is cos 30, which is equal to 0.87. And this is equal to cos 45, which is equal to 0.71. This is equal to cos 60, which is equal to 0.5. Now this is cos 120, which is equal to minus 0.5. And this is cos 135, minus 0.71. And this is cos 150, which is minus 0.87. And this is cos 225, which is minus 0.71. That means this side all are negative. The angular wave functions are negative. This angular wave function value depends on cos theta. So this side all the angular wave function values are negative, and this side all the angular wave functions values are positive. Therefore, this is positive and this is negative, and similarly in other cases. So the shape of the p orbital is a dumbbell shape and the lobes are along the axis. One is a positive, other is a negative. Positive because negative depends on the value of angular wave function. Next come to the shape of the d orbitals. Shape of d orbitals. The d orbital similarly depends on L or m value. L is equal to 2 for d orbitals and m is equal to how much? M is equal to plus minus 2, plus minus 1 and 0. That means 5 values. Corresponding to the 5 values of m, there are 5 d orbitals. They are designated as dxy, dyz, dzx and dz square, dx square and y square. let us see what are their shapes and what are their bond angles, what are the angular wave functions. So, the angular wave functions for dz orbitals now, these are the angular wave function for the 5d orbitals. The first, the m is equal to minus 2. The angular wave function for m is equal to minus 2 is 15 by 4 pi sin square theta, sin 2 theta, you can write sin theta 2 sin theta cos phi. So, sin theta and sin theta and this is your sin phi. This is your sin square theta and sin 2 pi, or you can say 2 sin theta cos phi. So, if you convert into polar coordinate into Cartesian coordinates, the value will be 15 by 4 pi xy divided by r square. Similarly, this is corresponding to m is equal to minus 1. The angular wave function is 15 by 4 pi half sin theta, cos theta and sin phi. Now, if you convert into Cartesian coordinates, 15 by 4 pi half, that is yz by r square. And similarly, corresponding to m is equal to plus 1, 15 by 4 pi half sin theta, cos phi, cos theta and cos phi, which is equal to 15 by 4 pi half xzy into xz by r square. Similarly, corresponding to m is equal to plus 2, the angular wave function is equal to 15 by 4 half sin square theta cos square phi minus sin square theta sin square phi, which is equal to 15 by 4 pi half x square minus y square by r square. Similarly, m corresponds to 0, 15 by 4 pi angular wave function is half 3 cos square theta minus 1 is equal to in Cartesian coordinates 15 by 4 pi half 3 z square minus r square 1 by r square. So, these angular wave functions depends on the value of xy, this is yz, then zx and x square y square and z square. So, when these angular wave functions are plotted against the coordinates in a 3-dimensional space, we will get the shape of the orbitals. This is xy plane, this is yz plane, xz plane, and now we can show these are this correspond to dxy, this wave function correspond to dxy orbital, this correspond to dyz orbital, this correspond to dzx orbital, and this correspond to dz square y square orbital, and this correspond to dz square orbital. So, the shapes of the orbitals are two dumbbell shapes, and the lobes, whether it is a positive sign or a negative sign, it depends on the value of x and y. Now, here the lobes are positive or negative sign, it depends on the value of x and y. If both is positive, then the lobe is positive. If both are negative, then the lobe is, so sign is equal to positive. If one is positive, other is negative, the resultant slope will be equal to negative. So, let us see the shape of the orbitals. Dz, this is your xy orbital. So, lobes will lie in between x and y. So, this is the lobes will lie x and y. This lobe will lie between y and z. So, this is y and this is the z. So, lobes will lie along y and z. Here the lobes will lie z and x. So, this is a z and x. So, the lobes will lie along z and x. Then there is another x and y. So, these have one sign. two lobes have one sign. This is positive, positive. This is the positive, positive. This is the positive, positive. I will tell why positive, positive. Then this is also another x and y. So here is lobes with x and y. Here is the lobe x and y. Here is the lobe x and y. So this is negative, and this is negative, and this is negative. So this is the shape of dxy, dyz, and dz. So the sign positive, negative depends on the value of x and y, y and z. If x is positive, and y is positive, then xy will equal to positive. If x is positive, y is negative, then xy will equal to negative. In this way, similarly for yz and zx orbitals. So the sign depends on the value of x and y. Let us see other three orbitals, shape of the other three orbitals. What are the other three orbitals? There are three orbitals, there are other two orbitals, dx square and y square. Here the lobes will lie along x axis and y axis. And dz square. So here dx square y square, the lobe along x axis is always positive. So this is positive and this is positive. Along y axis is always negative. So this is negative and this is negative. Similarly, dz square, the lobe along z axis is positive. So this is positive. And the ring is around negative. So this is negative. So these are the shape of sp, df, d orbitals. Similarly, shape of f orbital. We cannot show in this f orbital. There are 7 f orbitals. 7 f orbitals, but we cannot show in the blackboard. It requires a 3-dimensional picture to demonstrate the shape of the f orbital. So we cannot show here. So we can only show the s orbital, shape of s orbital, shape of p orbital, and shape of d orbitals. So we have already shown the radial and angular wave functions and the shape of the orbitals. Now let us come to the Pauli's exclusion principle. Now let us see the Pauli's exclusion principle. No two electrons in an orbital have same 4 quantum numbers. No two electrons in an orbital have same 4 quantum numbers. Now, for example, n is equal to 1. When n is equal to 1, it is a K cell. So K cell contains 2 electrons. Let us see what are the quantum numbers. One is n is equal to 1, L is equal to 0, its m is equal to 0, and s is equal to half. The another electron, n is equal to 1, L is equal to 0, m is equal to 0, and s is equal to minus half. So these are the 2 electrons in K cell. 2 electrons in K cell. So 2 electrons, that means in s orbital. In s orbital there are 2 electrons. The L is equal to 0 means it is s orbital or s subshell. So 3 quantum numbers may be same, but 4th quantum number is different. This is known as Pauli's exclusion principle. Why it is called Pauli's exclusion principle, I will tell later. Let us see how to calculate maximum number of electrons in a cell. So Pauli exclusion principle will help how many number of electrons maximum can be accumulated in a cell. Let us see how we can calculate the n value, L value, M value and S value. This is name of orbital, number of electrons in orbital, total number of electrons in a cell. Now n is equal to 1, then L will equal to 0, then M will equal to 0. So S may be plus half and S may be minus half. So what is the name of orbital? Depends on L, that is equal to 1s orbital. So number of electrons in 1s orbital is, that is equal to 2. So total number of electrons in cell means your K cell. How many electrons in K cell? That is equal to 2. Now let us take n is equal to 2. When n is equal to 2, what is the value of L? L may be n minus 1. That means 1 and 0. So L may be 0 as well as the 1. L may be 0 as well as 1. When it is 0, M will be equal to 0, S will be plus half and minus half. What is the name of the orbital? Is 2s, because the n is equal to 2. What is the number of electron? Is 2. In the cell, that is equal to L cell. Number of electron cell will not complete now. When n is equal to L is equal to 1, then M will be equal to plus 1, maybe minus 1, maybe 0. When a plus 1, there are 2 electrons, plus half and minus half. Minus 1, there are 2 electrons, plus half and minus half. 0, there are 2 electrons, plus half and minus half. So this is equal to 1 means here 2p. So 2p orbital contain how many electrons? Altogether there are 6 electrons. So what is the number of electrons in the cell? L cell, that is equal to 8 electrons. Similarly, if you go n is equal to 3, we will get 18 electrons. So we'll arrive a formula. The maximum number of electrons in a cell is equal to 2n square. So n is equal to 1 when n is 2n square. 2n square. When n is equal to 1, that is your K cell. So this is equal to 2. When n is equal to 2, it is L cell. This is equal to 8. When n is equal to 3, M cell equal to 18. So we arrive this conclusion that the total number of electrons in a particular cell is 2n square. Therefore, this is derived from Pauli exclusion principle. So it is called exclusion principle, means it excludes the possibility of accommodating more than 2n square electrons. So a cell cannot accommodate more than 2n square electrons, that is why it is called exclusion principle. Next is the Horn's rule of maximum multiplicity. The rule tells their pairing of electrons takes place after each orbital contains one electron. Suppose we say suppose it is P3. Pairing only takes after each contains a 1 electron. Suppose P3, we can write this and this, or we can write this and this, or we can write then which is the correct way? That is can determine from the Hund's rule. Now look at here. These 2 electrons can be pair, then it is 1 electron. But how to verify? Because the more, it is called Hund's rule of maximum multiplicity. If the system has maximum multiplicity, it becomes a more stable state. So multiplicity, what is the multiplicity? Multiplicity is equal to two S plus 1, where S is the total number of spin, that is twice S plus 1. Now look at here. Here 2 electrons are pair. Here half minus half, 0. So multiplicity S is equal to 0 plus half. So each spin is half. This is plus half, this is minus half, and this is your half. So 2 half plus 1, that is equal to 2. Now here the multiplicity is equal to 2 half. 2 3 by 2 plus 1, 4. Here this is really plus half minus half, cancel only half. So 2 half plus 1, that is equal to 2. Here plus half minus half cancel and 1 is minus half. So that is equal to 2 half, we can say half plus 1, that is equal to minus half, that is equal to 2, 1 plus 1, 2, that is equal to 2, it is a minus 2. So which is not possible. So which is the right form? According to Hund's rule, that the arrangement with the maximum multiplicity is equal to correct form, because it contains 4, maximum multiplicity is 4, here it is 2 and 2, so these are not possible, and this is possible because it is a more stable state. Suppose there are 5 electrons in a d orbital. Suppose they are d5. So we can write like this, or we can write, so here the multiplicity is equal to 2s plus 1. This is equal to 0, this is 0, half plus minus half, this is 1 half. So 2 half plus 1 is equal to 2. Here plus half plus half plus half, 2 5 by 2 plus 1, that is equal to 6. So maximum multiplicity is here. So this is the most stable state. Suppose there are 4 electrons in a p orbital. So suppose it is p4. Then here the multiplicity is equal to 2, 0 plus 1 is equal to 1. And here it is 2, 1 plus 1, half plus half, 1. So multiplicity here is 3 and here it is 1. So this is the most stable arrangement. That means the pairing starts. Suppose there are 4 electrons. We first fill up all the orbitals. Then pairing starts here. Suppose there are 5 electrons will be here. Then there are 6 electrons will be here like this. So pairing starts after each orbital contain 1. That's why it is called Hund's rule of spin maximum spin multiplicity, means the maximum multiplicity state is a most stable state, that is a allowed state. Then it is called above principle. Abba is a German What means building up? How to build up electrons in an atom? So the electrons are filled up in the different orbitals according to their increased energy levels. Electrons are filled up. Electrons are filled up according to increase of energy levels. Electrons are filled up according to increase of energy level. Lowest energy level is filled first. Then higher energy levels. So the lower energy level or higher energy level decided by N plus L rule. That is called N plus L rule. What is that? Number one, what is N plus L rule? Lower value of N plus L is the lower energy. Let us see 3D and 4S. In 3D, what is N plus L? N is equal to 2, L is equal to 2, that is equal to 4. Here N is equal to 4 and S is equal to 0. The value is, here N is equal to 3, here N is equal to 3 and D is equal to 2, that is equal to 5. Here N is equal to 4, S is equal to 0, that is equal to 4. So according to this rule, the lower value of N plus L is filled first. So 4S is filled first, then 3D. Second case is when N plus L are same. When N plus L are same, the lower value of N is filled first. Let us see 3P and 4S. Here 3P, N plus L is equal to 3 plus 1, that is equal to 4. Here 4 plus 0 is equal to 4. So in both the cases, the N plus L is equal. So which will be filled first? Lower value of N means 3P is filled first, then comes the 4S. Now let us see how to fill up by the order of filling of the orbitals. So first is your 1S, then 2S, 2P, then 3S, 3P, 3D, then 4S, 4P, 4D, 4F, then 5S, 5P, 5D, 5F, 6X, 6P, 6D, 6F. Now which fill up is according to this? First 1S, then 2S, 2P, then first 1S, then it come to here, then 2S, 2P, then 3S, 3P, then 4S, 4P, 4D. This is the sequence of arrangement of orbitals and filling of the electrons. First 1S, then it is filled with the, then here 2S, then 2S, then 2P, then 3s, then 3p, then 4s, then 3d, 4p, 5s, like this. So, these orbitals are filled. This is followed n plus L rule, how to fill up the orbitals. Now, these are the ways of filling up the electrons in different orbitals, the sequence of filling up the orbitals. Then what are the limitations? There are some limitations. First limitation is, so if you go on filling in this sequence, for chromium 24, the outer electron for chromium 24 is 3d4 4s2 fill up. If you go on the following the above principle, the chromium 24 electrons will fill up and the outer electron will be 3d4 and 4s2. But the actual this is not stable state, therefore it will become 3d5 and 5 4s1. Similarly, if you take the case of copper 29, according to above principle, this will be first fill up with your 4s, then the 3d, so this will be equal to 3d9 and 4s2. But the actual stable state is equal to 3d10 and 4s1. So, the actual configuration is 3d5 4s1 for chromium, and for copper is 3d10 4s1 because it is a more stable state. Half filled and full filled state are more stable state. I will tell later on why half filled and full filled are more stable state. This is one exception. Second exception is the ionization energy of iron. So, iron is 26. So, this is 3d6 4s2. So, if electron is lost for ionization, suppose it is converted to iron 2 plus. So, iron 2 plus, the electron is lost, that is equal to 3d and 4s. So, electron is lost from here, that is it will be 3d6 4s0, not 3d4 4s2. So, this is one exception, that in ionization the outer electron is lost, but this is not outer electron. But according to the this electron is lost, this is your inner electron. But according to above principle, this is here 4s2 is filled first, then outer is equal to 3d6. But electron is to be lost from here according to above principle. But the electron is not lost from here, this is not, but electron lost from here. So, this is second exception. The third exception is molybdenum as well as the silver. In molybdenum and silver, now look at the exceptions. In case of molybdenum, silver, gadolinium and gold. In molybdenum, according to above principle, it is 3d4 5s2, but it is to most stable state is your actual state is 4d5 and 5s1, because I have told you that half filled state is more stable than the less than half filled state. Now, similarly silver, just like your chromium and copper. So, similarly silver, the 4d9 and 5s2 according to above principle, electronic configuration, outer electronic configuration. But actually is 4d10 and 5s1, because filled cell is more stable than the complete cell. Complete cell is more stable than incomplete cell. Now, here the gadolinium, here it is 4d8 and 5s0, but most stable state is half filled, that is equal to 4f7. So, it becomes 4f7 and 5d1. Similarly, here it is 4f14, it is filled up, and 5d9 6s2. So, this is changed to 5d10 and 6s1. So, these are the according to the above principle, but stable state or actual state is this. Therefore, this is an exception. The another exception is the actinides and the lanthanides. In case of lanthanides, so in case of lanthanides, lanthanide is 57. The outer electron is J-non configuration and 5d1 6s2. So next electrons will go to the 5d1, then 5d2, 5d3, 5d4. Instead of that, it is going to the f orbital. It becomes 4f1, 5d1 will remain same, 4f2, 4f3, 4f4 like it, up to 4f14 instead of going to 5d. So this is also goes against the above principle. This is similarly also actinides. So these are the deviations or limitations of above principle. Thank you to all.